Hello, discrete math fans. We're on to equivalence relations now. Now we all have a sense about rational numbers that are equivalent to each other. These rational numbers, they all look different, but in fact they're the same number. So 4/15 is the same as -8 over -30. And it's the same thing as 40 over 150. And obviously, 4/15 is equal to 7,919,292 over 29,697,345. I mean, this is obvious, right? So all of these are the same, they just look different. So this idea of grouping things together that look different but are really the same, that's going to be our main idea behind equivalence relations. There's going to be an equivalency that we're going to be looking at. I'd like to remind you about the definition of a partition. A partition of a set A is a collection, it could be finite or infinite, of non-empty, mutually disjoint sets whose union is A. All right, so there's basically three key things. These sets have to be non-empty, they have to be mutually disjoint, and the union has to be A. We're going to create a relation from a partition. Later on, we're going to go the other way around. So here's the definition. So if we have a partition of a set A, the relation induced by the partition is defined on A as follows. We're going to say that for any x and y that's in the set A, we'll say that x is related to y if and only if there is some subset A sub j of the partition such that both x and y are in A sub j. All right, let's take this as an example. I've got a set A, it's got 1, 2, 3, 4, 5, 6, and I'm going to give you this partition of A. So this is a collection of subsets of A. Each subset is non-empty, the union is A, and these things are mutually disjoint. Let's find the relation that's induced by this partition. All right, we know that 1, 3, 4 is a subset of the partition. So we need all of these things in the relation. So for example, 1 is related to 3 because 1 and 3 are both in this set. 1 is related to 4 because both 1 and 4 are in this set, and so on. Now we also have to include the fact that each element of this set must be related to itself. So we're going to say that 1 is related to 1 because both 1 and 1 are in the set. And we'll do that for each one of these. So 3 is related to 3, 4 is related to 4. Now let's use the fact that 2, 6 is a subset of the partition. So now we're going to have all of these. 2 is related to 6, 6 is related to 2, 2 is related to 2, 6 is related to 6. And one more. 5 is a subset of the partition, so we need to say that 5 is related to 5. Now we can put all this together to get what our relation is. So if I collect all the things that we had said before, this is what's going to be in our relation. Now it's not hard to see actually that this relation is reflexive, symmetric, and transitive, and in fact this is true anytime we have a relation that's induced by partitions. So we're going to state that as a theorem. Let's let A be a set with a partition, and let R be the relation that's induced by the partition. Then R is reflexive, symmetric, and transitive. And we're going to prove this now. All right, so the proof goes like this. Let's suppose that we have a set A with a partition. Now let's go ahead and simplify the notation in the proof. We'll assume that the partition only consists of a finite number of sets. And the proof for an infinite partition, it's basically the same, it's just the notation is different. We want to focus on the idea here. So let's denote our partition subsets like this. All right, so A1, A2, A3, up to AN. These are the sets that are in the partition. So let's remember what that means. It means that the intersection of each pair of these sets is empty. They're mutually disjoint. And when we take the union of these guys, we're going to get A. This is all by the definition of a partition. So the relation R that's induced by the partition is defined this way. We're going to say that for any x and y in A, x is related to y if and only if there is a set A sub j in the partition such that x is in A sub j and y is in A sub j. So you've taken your set A, you've chopped it up into some pieces, and how do you know if any two things are related? They have to be in the same partition cell. Okay, so let's now prove that the relation is reflexive. Let's let x be an element of A, and we know that we have a partition of A. That means x has to be in one of these sets. But then we have a statement which says there is a set A sub j of the partition such that x is in A sub j and x is in A sub j. That statement is true. And so, by definition, x is related to x. And that proves that R is reflexive. Okay, we've got reflexive. Let's prove symmetric. Now let's let x and y be an element of A. Let's suppose that x is related to y. That means there has to be some subset of the partition such that x is in A sub j and y is in A sub j. But then if we take this statement, there is a set A sub j of the partition such that y is in A sub j and x is in A sub j. Well, that statement is also true. And so, by definition, y is related to x. Now we've proved that R is symmetric. All right, last one. We're going to prove now that our relation is transitive. Let's let x, y, and z be elements of A. Let's suppose that x is related to y is related to z. What we want to do is prove that x is related to z. All right, so by the definition of our relation, there have to be subsets ai and aj of the partition such that x and y are in ai, that's because x is related to y, and y and z are in A sub j, that's because y is related to z. All right, so what we need to do now is to show that x and z are in the same subset of the partition. We're going to do that by proving that, in fact, A sub I has to equal A sub j. All right, let's do this by contradiction. Let's suppose that A sub I is not equal to A sub j. We're going to come up with a contradiction. So, we know that A sub I intersect A sub j because this is a partition. And when we have two different subsets of a partition, they have to be mutually disjoint. Now we know that y is an element of A sub I and y is an element of A sub j. And so now we know that A sub I intersects A sub j is not empty, which contradicts the fact that we knew that it was empty. So it must be that A sub I is equal to A sub j, and so we know that x, y, and z are all in the same cell of the partition, and in particular, x and z are in A sub I. That tells us that x is related to z. So our conclusion is that R is transitive. That's what we were out to prove, is that R is reflexive, symmetric, and transitive. Okay, that's all for now.